Okay, so yes, this will be a talk about HYPRE. It's a library of parallel sparse linear solvers, focusing primarily on preconditioners and in particular multigrid methods. So let's get started. Before I get started, this is the team right now, currently, and we have a number of former members who've worked on the package in the past. You can get more information about the package here, in addition to what I'll talk about today. So this is the outline of what I want to do. I'll give a brief introduction and motivation, mainly about multigrid methods and why we care about that so much in this package. And then I'll focus largely on this conceptual linear system interface idea that we have in HYPRE. It's somewhat unique to the package. And near the end, I'll tell you a little bit about the solvers and preconditions that are available and give some additional information. OK, so some motivation first. Why multigrid? So multigrid methods, if you don't know, are called optimal methods. So if you have n unknowns you're solving for, they take order n computations to solve for them. And that gives them the potential to have really good scaling properties. So in particular, if you think of weak scaling, where you're growing the problem size with the number of processors, as sort of in this cartoon here, you have the potential to get constant time to solution for these larger and larger problems. Whereas many traditional and classical methods can be affected by condition number and other things and take more iterations, so they'll take longer, even though you have more resources that you're throwing at the problem. So this is why we care about multigrid. And just to give you a quick cartoon about sort of the main aspects of multigrid and why it works, think of a two-dimensional grid and a Laplacian problem you want to solve, for example. You have an initial guess, because it's an iterative method. So if you plot the difference between that and the exact solution, the initial error might look something like this. So the first main component of a multigrid method is a smoother or a relaxation method, something like Gauss-Seidel or a weighted Jacobi. After a couple of iterations of this, at least in the classical setting, what happens to this underlying error is it gets nice and smooth. And so what multigrid does is approximate it on a coarser grid. You can do that very accurately and, of course, more efficiently because it's a coarser grid. Solve for that, you interpolate back to the fine grid, and you can make very rapid progress towards a solution. Now, in practice, this can still be a huge linear system. So the way we actually do this is we just reapply the same idea. You do relaxation a little bit, makes the error even smoother still. You go to coarser grid, relax, coarser grid. And a lot of times we'll go down just a single degree of freedom. And then you interpolate all the way back up, do some additional smoothing and relaxation on the way up too, potentially. This is called a V-cycle. That's one of the various cycles you can have in multigrid. There are lots of other different cycling strategies. This is one of the best ones for parallel computing, so it's what's used most often. OK, so that's just quickly about multigrid. Now we'll actually just jump into the package HYPRE and how we use it. OK, so just from a very high level, before you start writing the code, you just have to make a few decisions. The first thing is choosing this linear system interface that I'll talk about. Then from there, you choose a solver preconditioner. Once you've made these decisions, you have some sort of underlying storage format that you need to choose based on that. And then the basic steps are sort of here. You build some auxiliary structures, possibly, like grids and stencils I'll talk about in a minute. Then you build the system, the matrix and the vector for the system, the right-hand side. Build the solver preconditioner, solve the system, and get the solution out. Those are sort of the basic steps for using the package. OK, so what about these conceptual linear system interfaces? This is another cartoon to kind of illustrate what the whole concept is, and also to try to show you why it's sort of useful and important to the package. Across the top, each of these little icons, think of it as representing a different interface for setting up a linear system. The one on the right is the traditional one you normally see for a linear solver package. This is an interface where you say, I want row 2, column 4 to have this non-zero coefficient. OK, so it's very matrix-based. And from here, you can get something like a general underlying. You can build a general storage format like compressed sparse row. And you can apply some sort of general technique like algebraic multigrid to it. But you might have a problem that has a structured grid. And you do a discretization on there, and you get a stencil. And this is something that's more natural for you. And we have interfaces that provide a more natural way of describing that linear system. From there, we can actually use the additional information to do something like a structured multigrid solver, because we have the actual information, and we can also store things differently underneath. So that's one of the advantages. At the same time, you could just as easily build a compressed sparse row matrix without doing anything different. The interface calls would still be the same, and still have access to general solvers as well. So it gives you a little more of a natural interface for the application that you're using, plus it gives you access to solvers that you might not have access to otherwise. And that's why we do this in HYPRE. And this is just reiterating some of what I said. OK, so in HYPRE, we have 4 of these things. And they have these names here. Struct is for structured grids. SStruct is for semi-structured grids. These are the 2 I'll talk about today, briefly, in some quick examples. And then we have one for finite elements that we support. It wasn't developed at Livermore. And we have our own version of the standard linear algebraic interface. So let's just get started with the first one, the structured interface. This is appropriate for scalar applications on structured grids with some fixed stencil pattern. Okay? And just to introduce some notation, we have something we call an index space. This is not uncommon in sort of AMR type packages and things like that. And it's just a collection of tuples, 1D, 2D, or 3D triples, depending on the number of dimensions. And then we have another notion called a box, which is just a collection of these indices. So down here, you can see you have an index space in the background. This is like your canvas. And then here are 2 boxes. The first one has a lower corner of -3,2 and the upper corner of 611. OK, so we use these index spaces and boxes to describe grids in this interface, as well as in the semi-structured one. So there are 4 basic steps in Struct for doing this. The first, the 4 basic objects you have to build: a grid, a stencil, then your matrix, and your vector. And just to illustrate how this works, I'll just give a simple Laplacian example on a 2-dimensional grid. And this is the grid that we'll use. It's a cell-centered problem. Assume it's partitioned on 2 processors for this example. One thing I want to point out is that as far as partitioning is concerned, in HYPRE, we don't do the partitioning for you. The user decides that. You just tell us what the partitioning is and describe the problem to us in that parallel form. But this is what we'll do for the example. And we'll look at the point of view of processor 0 in the code that I'll show. And I'll have a lot of these little movies that I'll be running through rather quickly because we're short on time. And what it'll do is have some code at the bottom, and then some sort of picture that demonstrates what's sort of going on, so you can see what's happening. So for setting up the grid, the first thing you do is call this struct grid create. You tell it I have 2-dimensional problem, and it gives you back a grid object. Okay? And then you make these calls to set extents, giving it a lower and an upper corner. So if I give it this lower corner and that upper index, then I tell it I have data that belongs to that box. I can do it again and tell it more about my local grid that I own on my processor. And then the last thing I do is call a symbol, and I'm done. And processor 1 does something similar for its part of the grid. Okay? So that's the grid structure. Then we have stencil. In this case, it's a 5-point discretization. Again, we have a create call. You tell it the number of dimensions and the size of the stencil, 5-point in this case. And then there's 5 calls to this set element call where you give it the entry number you're setting and it's an offset. So the center coefficient is 0, 0. Then you call it again. The west coefficient is -1, 0. East is 1, 0, et cetera. Okay? And that describes a geometrical shape for your stencil in your discretization, okay, on the grid. And that's it. There's no symbol routine for the stencil. So now I've got some structure information. I've got a grid and a stencil. Now I put it together to define a matrix. And I don't have a little movie here, but the calls in red are the basic calls for setting up a matrix. There's a create call as before. You have to make this initialize call. This just tells HYPRE you're ready to set some coefficients. And then the set box values calls is how you actually set the coefficients of the matrix. So in this case, I'm setting coefficients on these 2 boxes in each of the 2 calls. And I'm only setting the center and the south coefficient in this example just to show that you can set 1 coefficient at a time, 2 or 4, whatever. It's up to you. And there's going to have to be some boundary condition fix up normally, and then you call a symbol to finish the assembly of the matrix. To do the boundary condition, for example, you still make set box values calls along the actual physical boundary. And for the case of Dirichlet boundary conditions, you will tell it the south coefficient is 0, for example. Okay? For the vector, the calls are similar. You have a create and initialize, set box values again, and a symbol. The only difference is you don't have any stencils to worry about here. You're just setting vector values. Okay? So after those basic steps, I've got a linear system. And I can now call solvers, pass that in, and call solvers that can take advantage of the structure that I just described through that interface. Another thing you can do is if you have a symmetric problem, you can add this call, just insert it, and we'll only store the upper triangle or whatever, half of the coefficients. That's just one extra feature. OK, so that was quickly the structure grid interface. Probably the most interesting interface we have in the library is this semi-structured grid interface. And this is sort of an extension of what I just showed you. It generalizes it in several ways. It's for problems that have a lot of structure in them, but they're not entirely structured. OK, so here's some examples. Block structured grids, structured adaptive mesh refinement, overset grids. All of these things can be described through this interface. The other thing this does that the previous struct interface does not do is it generalizes to systems of PDEs. So that we had scalar problems before. Now we can do systems like elasticity, et cetera. And we have different variable types. Before, everything was sort of cell-centered. Here you can have cell, face, node, edge, quantities, and you can combine them in all kinds of different ways. OK? So let's see. Some more. OK, yeah, the way this works is we have a notion of a part. Okay, so everything that's a part in this interface is a structured grid, just like I showed you. Okay, and then what we do is introduce something called a graph, which takes all these parts plus some additional information that describes how they're coupled together. And that can be a very general way of sort of relating the different structured parts. And I'll show you a couple of examples of how this can be done. You can define things in terms of both stencils, and also something new here is doing things in terms of finite element stiffness matrices. So there's a finite element approach to doing things. We have these calls. Graph add entries is our most general way of describing how parts are coupled to each other. And then there's this set neighbor part and set shared part. And these are other approaches that are usually good for block structured settings. And I'll show examples that will make that clear. These are the examples. The last one I won't really go through. I'll just sort of flip quickly. So everything's the same as before, except I've got this additional graph object. Okay? And here's the example we'll start with. Okay? It's a diffusion problem. And I've got a block structured grid down here. And this particular discretization has cell-centered quantities and face-centered quantities. Okay? So now I've got 3 stencils for this particular problem to describe. All right? So how do we do this? So the natural thing for this problem is to split it up into 5 parts, part 0 through 5. I've chosen to number them this way. And I've also chosen to distribute this on 5 processors, each processor having a single part. But again, this is completely up to the user. This is just to make it simple for this talk. OK, so let's start with the grid. OK, as before, you call create. You give it the number of dimensions, but also the number of parts now. We have 5 parts. And then you set extents as before. And that says what piece of that part I own on my processor. And now I also have to tell it what kinds of variables I have, since I don't just have cell-centered quantities. In this case, I have 3 different variable types: cell, X face, and Y face. OK? So this next step, so at this point, every processor's described a structured part, but there's no relationship between them at all at this point in the grid. And one of the ways you can relate the different parts is through this function called set neighbor part. And basically what we're going to do here is this call, you don't have to read all the details, basically says that this box of data, all the variables that lives on this box on part 3 are the same as all the variables that live on this box on part 2. So we have to give a description of the box that I've drawn here in terms of part 3's index space and part 2's index space. And that tells HYPRE that those variables are the same. So if there's any stencil couplings that go into those locations, it describes how the different parts are then coupled to each other in the discretization. Same thing for relating part 3 and part 4. You just make another call to this set neighbor part routine. OK, and then you assemble the grid, and we're done. All right? So this is one way you can do block structured grids. Let me make a few comments about this. When you make this set neighbor box call, set neighbor part call, some of the variables become the same. So this one, for example, this edge face variable, or face, what am I calling them here? Yeah, they're called face, I guess, in 2D. But it's owned or shared by both part 3 and part 2, okay? And another thing to note here is that there are different types of variables. So on part 3, it's an X face, it's on part, let's see, it's a Y face variable in part 3 and an X face variable in part 2. You don't have to know any of this stuff, but HYPRE has to deal with all these complications internally to sort of handle where all the data is and assign unique processors to own it when we do the linear solve and all these kinds of things. OK, so that was the grid. Now we have a stencil. The stencil is very much like the previous example. The only difference is that, so we create it, and then we make a bunch of set entry calls. The only difference is that you don't just give it an offset. You tell it what variable you're coupled to as well. And you just make these set entry calls, just as in the previous example, to describe a stencil. And that's one of the 3 stencils I need for this particular one. OK, let's see. Where are we now? OK, we're creating the graph now. OK. This is a new object now. We call create, giving it the grid we just defined. And now we have to tell it what our 3 stencils are. OK. We didn't have to do this for the structured grid case, but now we do. And then we say assemble. OK, so now we have the graph set up as well for this problem. So that's it. That's all our auxiliary structures we have to build. Now we set up the matrix and the vector just as before, and it's similar calls. You call set box values or add to box values routines for both the matrices and the vectors. OK. Now there's a finite element style approach to doing this as well that we just introduced. So here's some of the new routines that you need to do that. Most of them have FEM in the name, and some of the examples in the hands-on will actually go over this same finite element example that I'm going to show you right now. Here it is. It's on a star-shaped grid. It's a Laplacian problem. It's a nodal discretization, so I've got, for each element, I've got 4 unknowns, and so I can define a 4x4 stiffness matrix, and that depends on the angle of the grid, and everything else. And here it's natural, again, just to split the parts up, 1 per processor in the natural way I've drawn here. It just makes it simple. And if we run through the calls, you'll see we're going to do this from processor 0's point of view. Again, for the grid, you call create, just as before. You set the extents just as before. And you set the variables now. We only have a nodal variable type here, just as before. So one of the new routines now is we can define the ordering of the variables on an element. So here I've defined it to be 0, 1, 2, 3 with this call. And now, instead of doing set neighbor part, there's another routine called set shared part, which is very similar, almost exactly the same interface, where I can say that these nodal variables on this edge on part 0 are the same as the ones on part 1 on its edge. Same for between part 0 and 5, and same for that nodal variable right there on the bottom left. Okay? So I make this call set shared part that number of times, and that's my grid. All right? Creating the graph is as before. You say create, and then there's this one new call where you say graph set FEM, and all that does is tell HYPRE that I'm going to define this matrix in a finite element style. It's not going to be stencil-based. It'll be stiffness matrices instead. Okay? And you assemble the graph, and you're done. Matrices and vectors are very much as before. You now use this set FEM values or add FEM values calls instead of set values calls. And instead of passing stencil-based things, you pass stiffness matrices. Okay? Okay. This AMR example I won't go through, just to say that there is a catch-all graph add entries thing that can couple any kind of part together in any general way you can imagine. You want to go quick? Yeah.
So I was wondering how you handle the indexing. Do you have like a mapping? Does the user provide a mapping between the local
No.
indexing and the local?
The user doesn't. He's asking about mappings of indexing. You don't provide mappings of indexes. It's just a global index that you describe everything in, and you know, yeah. A lot of the difficulties of dealing with these kinds of problems and setting up matrices are all handled by HYPRE underneath. You know, putting a global ordering on things, and then ultimately building a compressed sparse row matrix and things like that. OK, yeah, I'll skip that. OK, I have to go quickly over solvers in HYPRE. All right. We have 4 different interfaces I just described, and this shows you the different solvers you can get access to. You can see that in the semi-structured case, we get access to basically all the solvers. The general ones like algebraic multigrid or parallel ILU methods, as well as structured grid, multigrid methods, et cetera. Okay? So it's just showing you how you can get access to the different solvers. The way you set up solvers is you call a create, you set some, it's very similar to what Barry showed for PETSI. You set some parameters, call setup, call solve, get the values out using the conceptual interface you've chosen, and then you destroy the solver when you're done. Here's an example of how you set up a preconditioned CG method with multigrid. We have structured grid, multigrid solvers. These use semi-coarsening, these 2 methods. We also have a completely algebraic multigrid method, Boomer AMG. And this, if you look at the slides later, this shows you how you can get access to these solvers, to which interfaces will give you access to them. This is for definite Maxwell problems. So this curl problem here with an edge element, an edge element discretization works very well. It actually calls Boomer AMG underneath the hood. And we also have non-multigrid methods, such as sparse proximate inverse solvers, as well as parallel IOU methods. And this is where you get the code. You can also see reference manuals and users manuals online. And configuring and building the library is, in theory, very simple. You type configure. There are some options if you want to set various options, and then make. I forgot to put this on the view graph, but we also have a CMake build system, which is nice for building things on Windows boxes. Everything's written in C in HYPRE, but we do have a Fortran interface. It pretty much mirrors the C interface. There's a natural mapping between the 2. And if you have questions, bug reports, anything, this is the email to send those things to. And that's it. Just 22 minutes.